Right, now that we are comfortable drawing direction angles and calculating the standard angle from them, we are going to look at an application, vectors involving airplanes and wind speeds to see what will happen to the actual direction of the plane. So we have an airplane traveling at a speed of 500 miles per hour. That is actually going to be our magnitude, the speed of the airplane, in the direction north 30 degrees west. So if we start at north, which is again 90 degrees, go towards west 30 degrees, we are going to calculate our angle for our standard angle from that by doing 90 plus 30 degrees and getting 120 for our standard angle. So we're going to get the standard angle for our airplane and then also the standard angle for the wind as our first step. The airplane reaches a certain point and encounters a wind velocity of 70 miles per hour. It's going to be the magnitude for the wind in the direction of north 45 degrees east. So we're going to start at north. We're going to go towards east. Now, the nice thing about 45 degrees is it's right smack in the middle. So when we do 90 minus 45, we are getting 45. So if you forgot to do the standard angle for this one and use the 45, you would be okay because they are the same. Most of the time, though, you want to make sure that you do that calculation. And then we want to determine a vector for each of those. So our speed is equal to our magnitude, which is the 500. So I'm going to call the plane P. It doesn't really matter what letter you use for these. You could use A for airplane. Will be 500 cosine 120i plus 500 sine 120j. And then our wind will be 70 cosine 45i plus 70 sine 45j. Now we're going to look at this visually and algebraically. The algebraic is obviously going to give us our correct final answer, but we want to add those two vectors. So if we think about what's happening here, here's the plane going along its merry way. It hits a certain altitude, and then all of a sudden the wind is pushing it or pulling it in another direction. It's really pushing it, but we do adding tip to tail. So technically what's happening is the wind is pushing, the wind is going this way. It's taking our airplane and it's going to move it in a new direction so that we get a new resultant vector of the actual ground speed of the plane, which is the ground that the plane is covering while it's in the air. So I'm going to call this G for ground speed. There might be a time where you're given the ground speed and have to find the wind speed instead. So just for the future, our plane plus our wind vector is going to equal the actual distance that's being covered on the ground. Although the plane itself is not on the ground, eventually it's going to a new location that is also on the ground. So the ground speed and direction is important because you want to get to that new location. So if we do our adding, we are adding those two vectors together. You're going to be doing 500 cosine 120 plus 70 cosine 45 in the calculator times I plus 500 sine 120 remember when you're adding, you're just adding the component pieces together. So the actual calculations with the vectors for these are not too challenging. It's the setup that is going to be the challenging part for this. When you add that up, you get the ground vector to be negative 200.5i plus 482.5j. Notice it's a negative and a positive, so our resultant is in quadrant 2. That will be important when we are calculating the direction angle later on. We want to make sure we get that angle in quadrant 2. All right, we want to find the actual speed or the ground speed. So we're going to do the magnitude of g that we just found. Make sure to use exact answers to calculate here. So you should have those stored from the calculator. And also in step 6. Which might mean scrolling back a little to grab those answers when you're doing it. So we're going to do square root of 200.5 squared. I'd make sure to put that in parentheses because you're going to be bringing that negative down with it. And then 482.5 squared. Again, those are rounded right now, so you're pulling those exact calculator answers down. And then you're going to get about 522.51 miles per hour. That is our ground speed. And then to find the actual direction, we're going to go back and do tangents. We're going to do tangent theta is equal to 482.5 divided by negative 200.5. That's going to actually give us a reference angle. I'm going to get rid of the negative sign that will come out from the calculator of 67.44 degrees. And since we're in quadrant 2, we will do 180 minus that. So we're bringing back some of our angle measurement things from the beginning of the year. Never quite goes away. So we have 112.56 degrees. Now we want to work backwards to come up with a direction angle. Here's north, here's west, here's 112.56. And because we are looking at north, we want to figure out now this inside part right here. So we would want to take 90 away from that 112.56. And that will give us 22.56. And then to write it, we're starting at north. We're going at 22.56 degrees towards west because we're in that northwest quadrant. So really just nesting that degree measure inside of the two things that are surrounding that quadrant. So in this case, north and west. If you're in first quadrant, you would use north and east. If you're in the third, you would use southwest. Fourth would be southeast. So we're converting in two parts. We're converting at the beginning, and then we're also converting back at the end to get those correct angles. So that wraps up our two different application types. Again, there might be a time where you're using ground speed. So remember, we did find ground speed earlier. If you're given this and the plane speed, you should be able to find the wind. You're just going to be doing subtraction. So just a little bit of a hint. Since ground speed is plane plus wind speed, ground minus plane would give you wind, or ground minus wind would give you plane. Those would be some different variations of that or you might have to do subtraction instead of addition in a similar problem.